So, Lab 8, it's actually a two-part lab. They're all in the same lab. It's all stellar distance, but the first part deals with parallax and the second deals with main sequence fitting. So I'm going to tackle those two things and give you a little bit of advice. I know this is kind of a weird transition to do things online, but hopefully this helps you. So here's our cosmic distance ladder. If things are really close to us, like really, really close to us, we can use radar. But after that, we start using parallax, which I'll explain what that is in just a minute. But eventually, things get too far away for parallax to even work, and so we have to use main sequence fitting. And sometimes main sequence fitting just isn't reliable, so we start using variable stars, which are incredibly reliable, white dwarf supernova, but for our purposes, we're just going to ignore those. We're not dealing with those today. So, this man here is Tycho Brahe. He was an amazing, amazing astronomer. He was eccentric and rich, and there are so many stories about him. The reason his nose looks all weird is he actually got into a duel, a sword fight, with another mathematician over a mathematical equation. So that's interesting. He lost his nose over it. I don't think he was correct about the equation, anyways. So he lost his nose for nothing. He did get a golden nose made for him to put on when like guests came and stuff. Um, you see a moose in the background. That moose is his pet. So he would host these parties, and one time the moose got drunk at one of the parties and fell down the stairs. So all sorts of crazy stuff with Tycho Brahe. Now the reason I show him is because he has this weird nose, and we can use this cool thing. It actually doesn't work too well on computer screens because I guess the computer's really close to you, but it does work pretty well if you just look across your room. What you're going to do is extend your arm completely and stick your thumb up like you're giving someone a thumbs up. And then you're going to close one of your eyes and focus your thumb covering something in your room. We used to, if your computer is far enough away, you could use his nose, but it doesn't work too well because it's really close to you. So you can focus on something or a corner of your room or something, closing one of your eyes and put your thumb over it, then switch eyes, and you'll see that your thumb looks like it's moved. Of course, you haven't actually moved your thumb, but it does shift a little bit. That's called parallax. Now I want you to keep doing that, keep switching eyes. Slowly move your thumb closer to your eyes. You will see a difference in the shift. Now, I said that this was called parallax. That's half right. What you're observing is the angular shift. The parallax angle is actually half of that. So, it's a little complicated, but we'll talk about it. Don't worry. So here, if you look on page 71 in your lab manual, you will see it says figure 1 and figure 2, and they kind of mimic this slide. So you'll notice it says stellar parallax, sky, angular measurements, because we can make angular measurements from the Earth. And we're going to try and locate on page 71 reference stars A and B, or stars A and B, using some reference stars that we already have. So for figure 1, it's set up very similar to this. You have the sun, you have the Earth. Over here is actually January on your paper, and you have to draw in, there's a whole procedure on page 70, but I'm just going to explain it to you in case that doesn't make sense. So you have to draw in Earth 6 months later, which it makes sense that July would be 6 months away from January, right? It would be on the opposite side of the sun. And then you're just going through the star. Make sure you have a ruler handy. You do need a ruler for this lab, so I hope you have that handy, not just for the straight edge, but you are going to be measuring things later. All right, so going from the Earth using your ruler, you're just going to draw a line through your star and keep that line going until you get to the background stars. Now, these background stars are the same as these background stars here. Don't be scared of them. It's okay that they are there. We're actually wanting to use these stars to figure out where this star looks in Earth's sky, right? You do the same thing 6 months later, so you draw the same line but going in the opposite. You'll see that this star looks like it has moved. What you'll do is mark that. Not only do I need to see all these lines being drawn, but I also need you to mark X's on this circle in figure 2. You're going to draw a little X where you see the star in the background stars. Draw it over here. Don't draw it on figure 1, draw it on figure 2. So you'll put a little X down. Since you will be doing this twice, I suggest doing one above and one below the background stars just to keep things nice and organized. So you'll draw both of your X's 6 months apart, right? And then you'll draw a line between them. This line is your angular shift. You'll do this again. One of these stars is further away than the other, all right? And just like how your thumb was, you can see that there is a larger shift when your thumb, I don't want to give you away answers, so just determine if when your thumb is closer to you, if you had a larger shift or a smaller shift, and that tells you which of these lines goes with which star. Just a little logic check for you. So make sure all of these are labeled. I know on our slides we don't have it labeled, but these do need to actually be labeled, like star A, January, or star B, January, etc. So make sure everything is labeled. They are worth points. All right. This next slide will really help you with question number 4 on page 74. Now, answering questions 1 through 3 first. There's information in between here, by the way, so read that. But answering questions 1 through 3 really sets you up for a good way to get to number 4 and how to solve it. This slide does not show you how to solve number 4, but it does help set up the problem to make it a lot easier for you. So here we have our star field, which looks very different than your number 4, so just be aware of that. It's not going to be the same numbers. We want to figure out how far away C and D are from each other by using information from A and B. We know that they are 28 arc seconds away from each other. All right, this double apostrophe here, that means arc seconds. So we can make a plate scale. We did plate scales a couple weeks ago. It was before spring break, I know. But you're going to need to get back into the swing of things, and you'll make this on your own. Now I'm going to show you how to make a plate scale with our example, but these are not the same numbers. I cannot say that enough. These are not the same numbers. Do not use my numbers. You will be wrong. So we know that they're 28 arc seconds apart. We're going to measure that in centimeters. So I have my ruler up here. We measure it in centimeters. It looks like it's less than 1 centimeter. It looks like it's about 0.8 of a centimeter. So we say that 28 arc seconds is equal to 0.8 centimeters. That gives us a beautiful correlation. Now, just like how there are 12 inches in 1 foot, we can convert. This is just a conversion factor now. And we are going to be measuring in centimeters right over here. So since we're measuring in centimeters, we'll be multiplying by our plate scale the centimeters. We want those to cancel out. So it tells us that we need centimeters on our plate scale to be on the bottom. So we divide over, and we see that this just equals 1. So you get some fancy-dancy number. Arc seconds over centimeters. That's your units. Do not forget your units. They're very important. All right, so that's our plate scale. Now we can measure from C to D in centimeters. I suggest measuring from the center of the star to the center of the star shape. Do not just measure the arrow. It'll be too short. So fully measure the star. Center to center is always best. All right, and here we see it's like 2.5, 2.6, so 2.5 centimeters times our plate scale. Our centimeters cancel out, and we are left with arc seconds with some number. Now this be careful, this is your angular separation, all right? It's your angular shift. It's not your parallax angle yet. In order to find your parallax angle, you have to divide by 2. Your parallax angle is only half for angular shift. I would do that now. After you convert into arcseconds, divide by 2 to get your parallax shift, your parallax angle. Now the next thing on number 4 is it wants it to find it in light years. You're currently in arcseconds. If you look on page 73, it tells you how to get from arcseconds into parsecs, and then parsecs into light years. And that's what questions 2 and 3 are all about. So, or I guess really question 2. That once you get it to this point, once you divide by 2, just follow the same steps you used for question 2. If you do have questions about number 2, or really any of them, please let me know. There is a discussion board open. I finally got that to work, so you can put your answers there, or you can just email me directly. I prefer to my JAX account, which is harrismc@jax.sfasu.edu. Please email me your questions or put it in the discussion board. Other people can help you in the discussion board, or I can answer questions and other people will be able to see it in case they have the same question as you. So do not be afraid to use your resources. I am here to help. I really want you guys to still succeed in this class. As long as you still put forth some effort, you'll do great. All right, moving on to the second part. This is the main sequence fitting. So this cluster up here in the corner, it's a beautiful little cluster of stars. It's incredibly famous. It's called the Pleiades. We use the Pleiades a ton in this course, so I want you guys to just be aware of it and know that that's a nice cluster. It's very young. We use it for a lot of examples. It's going to be your favorite cluster, I hope. I really hope. I love it. Alright, so here are some clusters, different types of clusters. We tried stellar parallax. Eventually, the thing about stellar parallax is once the star gets too far away, like if you could chop off your thumb and you move it away and keep doing like what you're doing, eventually the shift is just so small you can't even see it anymore, and it just becomes a background star, right? So it's not a very good method for when things get too far away. It's only good if things are close enough to us. So once they aren't close enough to us anymore, we can go to main sequence fitting. What this is, well, you remember main sequence from last week's lab, the HR diagram. We're going to be dealing a lot with HR diagram. We're going to be using it. Here's a quick review of the magnitude scale. So just like in sports, you want to be number 1, and in golf where you want to have the lowest score, the brighter a star is, the lower its number is. So if it's a very negative number for its magnitude, it is an incredibly bright star. If it's a very positive number, then it's an incredibly dim star. We can see up to magnitude 6, so that's not that far. There are lots more stars that we just can't see. You can see them if you have a telescope or a pair of binoculars, depending on the star and what its brightness is. But these are our magnitudes. In between each step of these magnitudes is a ratio factor of 2.512. This is multiplicative. That's a very hard word to say, I'm sorry. And I just had some dental work done, so talking is a little difficult. Bear with me. Alright, so if this goes one step, you just have 2.512. But if you go 2 steps, so now it's 1 to 3, you're going 2 steps here, then you multiply those together and you get 2.512 times 2.512, or another way of saying that is 2.512 squared. Right, so this is our little magic ratio number. Then if you do 3 steps, you cube it, etc. Now the reason we have this number is we said, hey look, there are 5 steps between 1 and 6. You can see things that are brighter than 1, by the way. There are 0 and negatives, but historically it was just all called 1. So that's how this came about. So historically they said, hey, 5 steps between 1 and 6. So we're just going to call that 100 and then take the fifth root of 100 and you get 2.512. So it's a little funky, but it works wonders. And this is just a table down here. You can see it equals 100 at 5. How perfect. Stellar brightness, again, some review. Apparent magnitude is denoted by little m, which means apparent. And the V down here, the subscript V, just means the visual spectrum. Sometimes you work in ultraviolet or radio or infrared, etc. So you might not always be in the visual spectrum. That's why we have the V there. You don't really have to write that down if you don't want to, though. That is the brightness from Earth. So it's how we see things from Earth. Its apparent brightness, basically. The absolute magnitude is capital MV, again, V standing for visual spectrum, and that is inherently tied to the brightness from 10 parsecs away. So it has a distance tied to it. So in the future, if you're using your absolute magnitude and you're trying to find distances, hint, hint, that's what we'll be doing, you're going to use 10 parsecs because it's tied to your absolute magnitude. Alright, so here's our inverse square law of brightness. We use this a ton. It's incredibly helpful. And here's just an example on how it works. We have a light bulb. We know how much energy the light bulb is giving us, aka its brightness. And it's 10 meters away from us, and we're measuring how bright it is, alright? We know how much energy it's putting out, and we see how bright it is. Those two things are related, right? But they're related specifically based on distance. So if we move this and we put it twice as far away, you would think that it gets twice as dim, but that's not actually true. What happens is you're saying it gets twice as far, so you take that 2 and you put the 2 in for the D meaning distance. The 2 comes from being twice as far, so 2 times as far. You square your 2 because your distance is being squared, you get 4. So it is 1/4 as bright, and you see this here, the light becomes 1/4 as bright. If you get 3 times further away, so 30 meters instead of 10, you always go back to your original reference point, by the way. So it's 3 times as far away from your original place. So 3 squared is 9, it's 1/9 as bright. Same thing with 4 times as far away is 1/16 as bright. Now, here's a little different way of using this. There's lots of tens and hundreds in this, so just bear with me. You have a 100-watt light bulb, so same light bulb, hasn't changed. It's now 100 times fainter. Another way of saying that, so this is 4 times fainter, or a quarter as bright. Another way of saying 100 times fainter is it's 1/100th of 1/100th fainter, right? So 1/100th is bright. It is still being compared to this original 10 meters, and we want to know how far away is it. Well, we know that this whole thing is 100. So how do you undo a square? Well, you take the square root of it. So make sure you have a calculator nearby that can take square roots. What is the square root of 100? Well, that's actually an easy one. It's 10. So now we know that it's 10 times further away. We can go one step further. We know that it's 10 times further than our original reference point, right? So 10 times 10 meters gives you 100 meters. So you know that light bulb is 100 meters away. We'll do the same thing with stars. We have a star, we're 1 AU away, we can measure its energy output. Now we're at some unknown distance away, but we know its energy output now. So we can make a ratio. We start with our original energy output, and then we divide it by what we see now. And we happen to get 4. Now we're going to use that 4 in our inverse square law of brightness. Just like what we just did, we take the square root of 4. It gives us 2, so we know we're 2 times further away than our original reference point, which was 1 AU. 2 times 1 AU is 2 AU. Another example, we're now at 55 watts per meter squared. So 1370 divided by 55 equals 25. Take the square root of 25, just like we just did, because the inverse square law of brightness is squared, so you have to undo that square. We know that we're 5 times further. That's our D now. Our distance is 5 times. 5 times our original place, which is 1 AU, so we're 5 AU away. Hopefully this is starting to make sense. Now we're going to deal with distance modulus. I hope you remember what this means. This is apparent magnitude minus absolute magnitude. It's very important that it's apparent minus absolute because the negative or positive sign matters. So here we're given some information about a star. It's a G25 star, just like our sun, and if this will go away, the absolute magnitude is 5, the apparent magnitude is 8, right? So this star, remember the larger number for magnitudes, which magnitude doesn't really have a unit, by the way, they're just magnitudes, or something can be like times, but it's not really a unit. There's not really a unit associated with it. But remember, the larger a number is, the fainter it is. So its apparent magnitude, so how we see it from Earth, is fainter than its absolute magnitude. So we can kind of guess, like, it got brighter when we put it at 10 parsecs. Therefore, we had to pull it into us, right? So it had to get brighter. So I think that it is further away normally. So let's check our work. We start at 10 parsecs. That's because it's inherently tied to 10 parsecs, the absolute magnitude. We want to know, is it closer or further? So we look at a distance modulus. You just plug your numbers in. You get positive 3. There are some rules about distance modulus. You might want to make note of these. They're very important. But basically, if your distance modulus is positive, then it is further than 10 parsecs. If your distance modulus is negative, then the star is closer than 10 parsecs, right? It's an easy way of remembering that. It's a lot of words, and it says it in a better way here, I guess, but it's easier for me to remember that negative means further away. But how much further? We're going to use our inverse square law of brightness, just like we had already done. So we use our distance modulus, which is 3 here. If this distance modulus, if it was like 8 minus 5.5, you'd be left with 2.5. You would use 2.5 instead of 3. It all depends on your distance modulus. It's okay to have decimals. I want to make that clear. Here we have whole numbers just because examples are nice, but in the real world you don't have whole numbers. You have fractions and decimals, and it's messy, and that's okay because you have a calculator to do all the work for you. You take your brightness difference of 2.512, that's our magic ratio. You raise it to your distance modulus, that 3 here is the distance modulus. It equals 16. You put that in a calculator, boom. Now, we're going to use our inverse square law of brightness, and we say it's 16 times fainter. So let's take the square root of 16. We're going to undo that square, right? We get 4. Now we know that it is 4 times further away than our original reference point. Our original reference point, because it's tied to the absolute magnitude, is 10 parsecs. So 4 times 10 parsecs is 40 parsecs. So we know that the star is actually 40 parsecs away. My initial guess that we had to bring it in closer to us to find its absolute magnitude, therefore it was further away, was correct. This slide is really, really helpful for your work because it's a lot of what you're going to be doing for page 78, question 1. It's split up into 2 parts. You use method 1 and method 2. I'll talk about that momentarily. Alright, so all that fun stuff. Here's one singular picture showing 2 different clusters. You have the Pleiades cluster, we looked at a little bit earlier, and the Hyades cluster. Interesting fact, this star here is actually not part of the Hyades cluster. This star's name is Aldebaran, meaning the red eye of the bull, and it is about half the distance away than the Hyades star cluster. It just happens to line up perfectly. So everything here except for that little star right there. Not little, it's actually very bright and large. But everything else is part of the Hyades star cluster, and it's about the same physical size as the Pleiades cluster. But this one looks a lot bigger to us, right? Well, there's a reason for that. It's closer. That's all, right? Like, when things look brighter, they tend to be closer to us. So we'll see how all this works. There's a couple assumptions that you have to make about stars in a cluster. It's really, really important that you understand that all the stars in a cluster are the same distance and age and chemical composition. No one cares about that one, though. Well, not for our purposes. Some people care about that. I'm going to go through this a little slowly so we can really understand why we can say the stars in a cluster are the same distance and age, and why that might matter to us. So for this lab, only one of these is incredibly important. So hint, hint, nudge, nudge, you might want to pay attention to that. We are trying to find the distance to stars, so it might be really helpful if we know that all the stars in a cluster are the same distance away from us. Hint, hint, wink, wink, nudge, nudge, whatever those words are. Okay. So the reason I can say that they're all basically the same distance away from us is if we were in a classroom with all of our class buddies instead of spread across the world and in our homes, we would all be about the same distance away from, say, Houston. One person might be closer to Houston than another, right? But it'll be a very small distance closer, incredibly small, basically negligible, right? So if we were to try and go to Houston all like in the same car, we would get there at the same time. It would be maybe a fraction of a second difference, but it would not be enough to warrant actually having to find individual distances super specifically. And precisely, we would be able to just group us all together and say that we were about the same distance away from Houston. Same thing with stars in a cluster, they're all about the same distance away from everything because they are in a cluster. They're very close together. And their age, they were all made from the same star materials, all the same dust and gas and everything. So they were made, chemical composition is the same, and their age, they're all made at about the same time. So those things all go together, but there are some differences in stars in a cluster. Stars in a cluster can be whatever size and whatever temperature they would like, which means that they can go anywhere on an HR diagram. It doesn't matter that they're in a cluster. They can be whatever size and whatever temperature they like. Want to be clear about that. Alright, so main sequence fitting, we have our Pleiades cluster, we have our Hyades cluster, and they're about the same size, about the same types of stars, but Hyades is a lot brighter. You can see relative apparent brightness, it's just higher in every place. How can we figure out what's going on here? Well, they're closer to us, and we want to know how far away the Pleiades is. Because they're a lot dimmer, we want to know how much further away they are from the Hyades cluster. We use our inverse square law of brightness. So we take that 7.5 times, we take the square root of it, you get some number, and that's how many times further away the Pleiades are than the Hyades. So if we knew the distance to the Hyades, we would multiply it by 2.73 times, and you would get how far away the Pleiades is. Okay, here we have a visual diagram of dust. You will need to know this information for many labs in the future. We're not taking it into account this time, but you will need to know it for the future. Different labs, your lab final, all sorts of stuff. You really need to know that there is this dust that's all between the stars and you. Dust and gas. And what happens is these dust particles really, really, really like to scatter light. In particular, they scatter blue light. So interstellar dust, it is going to scatter out blue light, and that has two effects for us. The first one is that we're not seeing as much blue light, we're seeing a lot more red light. so we think that the entire star is redder, and therefore we think that it's cooler. And the second effect is that because it's scattering light, you're not getting the whole intensity of the light. So it's not going to look as bright, and you're going to see just a little bit dimmer, right? You're going to see that star is just a little bit dimmer, and that dimness makes you think that it is further away. The further something is away from you, the more gas and dust are between you and that object, so the more you have to correct for it. This week we're not correcting for it, but next time we will. Alright, so here, this is in your lab manual. It is page 82. You have a standard main sequence. Good times, as absolute magnitude and color index. Hold on. So it is absolute magnitude and color index. Now you can see your main sequence line there, and we're going to move on. Now you have the Pleiades color magnitude diagram. Opposite side, this has apparent magnitude, right? So other one had absolute, this one has apparent. That's good. It gives us two different things of information, but they both have the same color index. Now, keep in mind, an HR diagram could have luminosity or absolute magnitude, but never apparent magnitude, so this is not an HR diagram. But the bottom part can be color index, temperature in Kelvin, or spectral classification. All those are acceptable substitutes for temperature. That's all acceptable ways to show temperature, so that any of those can make an HR diagram. We're going to be filling out number 9, get you some free answers, and show you how to do this lab. So you're going to get some information from your lab here, from this page. First things first, we're going to look at color index. So for number 9, if we draw a straight line down, we can see that that color index, it's after the 0.4, it's after 0.41, it looks like it's in between 0.41 and 0.42. So I'm going to call that 0.415, alright? So that's our color index. Try to be as specific as you can and get to 3 decimal places for all of these. The other piece of information you can gather, looking at number 9, is drawing a horizontal line straight across to see its apparent magnitude. This magnitude scale, just be aware that the numbers are reverse what you would expect. So it looks like it might be like 10.2, but actually it's going from the other way, so it's 9.8. Right? So we write down that its apparent magnitude is 9.8. Then we flip our page over, and you get to the main sequence. Now you're going to take your ruler again, you're going to go to where the color index is 0.415, you're going to draw a line up to your main sequence. Right? Because the color index is the same on both sides, we can easily translate them like that. Then from your main sequence, you're going to draw a line over to the absolute magnitude, and you're going to figure out what that absolute magnitude is. We say it's 3.6. You might see it as 3.7 or 3.5, and that's okay if it's a little different. Just, it should be in a general range. It's pretty small. Now we have all this information. If you see that you have your apparent magnitude and your absolute magnitude, the first thing that should come to your mind is distance modulus, because we love distance modulus. We subtract, we get our distance modulus, it's a positive 6.2, so we know that this star is in fact further away than 10 parsecs because it is positive. And now we can do some real cool stuff, like figure out how far away it is using that method we already did earlier, where you use the distance modulus, you raise 2.512 to your distance modulus, that whole thing, and you use inverse square law of light. That's what you're doing for question 1, both parts of it. All right, so you're going to do this multiple times for all the different stars on page 77. If I can flip the page. So you're going to do stars 9, 18, 20, 22, 27, 31. Then you're going to average the distance modulus at the end. So you'll add all this up, divide by 6, you'll get your average. use your average distance modulus for question 1, where it asks for distance modulus method 1. Just write down the average number there. I'll give you a hint. It should be around the same number. They shouldn't be too drastically different, right? Then it says method 2, and we're going to cheat a little bit for method 2 because we don't actually have overlays now. You have to just go with me on this. We're not in class, we're doing online stuff, and this is just a little complicated, and I wanted to show you a really nice, easy way to do this, alright? So here in the PowerPoint, this green paper here is meant to represent the paper of the standard main sequence. It's not the same as what is in your lab manual. It was a different paper altogether that we would have given you. And this black thing here that says Pleiades color magnitude diagram is an overlay that we would have given you as well. What you do is you line up the zeros on the bottom of the color index on the overlay with the paper, and then you move the overlay up until the cluster fits right along the main sequence. And then you notice how here on the paper there's a 0 right here. Keep in mind where that is. So we move this over, move it up, and that 0 hasn't changed anywhere, it's still there. You're going to just read off what the overlay number is. In this case, you can see it's between 5 and 7, therefore it is 6. Some people would say it's like not perfect, so maybe it's 6.1, 6.2. Here I say it's 6.0. So you can use this for method 2. We just did it. You don't have to actually do it yourself because we just did it on the PowerPoint for you. That is my advice to you for method 2 to be able to use that. Then you're just going to do the same for question number 1. It's split up into 2 different parts for method 1 and method 2. You're just going to use the distance modulus you just found, which is this, and do the same process as you do for method 1, where you do the 2.512 raised to the distance modulus, etc. So that is all I have to say about that. For question 2, I told you some good information about all of that. Question 3, question 4. Oh, for question 4, make sure it says to explain your reasoning. Those are really great reasoning. If you look into this slide back here, I'll just bring it up. If you can use this information, it might be really helpful to you. I went too far. Getting there. This information can be really helpful for you. And I also mentioned stellar parallax stuff. So that is all the information you should need. If you have any questions, please do not hesitate to ask me. There's discussion boards. You can email me. You can do all sorts of things. Please, please, please ask your questions. I think every single one of you can still succeed in this class, even though we had to go into an odd format. I think you're still going to do great as long as you put forth the effort. You will be fine. Make sure that you are staying safe, practice social distancing, wash your hands, try not to touch your face. It's really hard for me to not touch my face. I know I constantly do it, but just try your best. Make sure you wash your hands at least 20 seconds, all that good stuff. Make sure you get your nails, whatever. Be safe, and I hope you have a great rest of the semester. Alright, bye.